So our first speaker today is Stephanie Douglas. She got her PhD at Columbia. She's now an NSF fellow at the CFA. And today she's going to tell us about the impact of companions on stellar rotation. So take it away.
Great. Thank you all for getting up after Astronomy on Tap. Assume you guys are the ones who didn't party super hard last night. But yeah, I'm an NSF fellow at the CFA. I'm in my third year there. And my research focuses on the evolution of stellar rotation, and especially what I'm interested in right now is how stellar companions affect that rotational evolution. And I'll just take a second to acknowledge many of my collaborators, and many of these collaborators actually either currently or in the past have had a tie to UT. So as I said, the big question that I'm trying to answer is how does stellar rotation evolve with age? There are kind of three sub-questions that we can look at here. One is, can we accurately predict the rotational evolution of stars, especially low-mass stars like M-dwarfs? What does that rotational evolution tell us about stellar magnetic fields? And how do companions affect a star's disk and its rotational evolution? So the reason why we should care about rotational evolution at all is because of trying to understand planets. So we only understand any planet as well as we understand its host star. So we're used to thinking about this in terms of things like the radius of the planet, because that depends on how well we can determine the radius of the star. But it also comes down to things like how much high energy radiation is the planet receiving, which is tied to its rotation, or how old is it. So young planets are probably pretty inhospitable. This is an artist's conception of early Earth. So there's probably no oxygen in the atmosphere. There's a lot of asteroid and comet collisions happening, heavy geologic activity. Older planets, on the other hand, are probably a little bit more pleasant. Though, of course, that depends on who you ask and when you ask them. Winter is coming to Boston, so ask me in a month. So the challenge that we have here is how do we determine the age for an isolated field star if we find a potentially habitable planet around it? So this is just standard isochrones. So the lines correspond to each line corresponds to all stars of a variety of masses at the same age. Lower curves are older. So a high mass star evolves fairly quickly. So if we can determine its temperature and its luminosity, which we can for most stars in the Gaia era, we can figure out its age with reasonable uncertainties. For something like a solar mass star or a K-dwarf, these things basically don't evolve while they're sitting on the main sequence. They stay at the same temperature and the same luminosity for billions of years, maybe more than 10 billion years. Definitely more than 10 billion years. So how do we determine how old these stars are? So first, one way we can determine stellar ages is for clusters. This is isochrones again. This time shown, the points are Hyades stars. So the Hyades is our closest open cluster neighbor. And you can see that when you've got all these stars of different masses, you can fit an isochrone to them, or lay isochrones over it and sort of fudge which ones fit best to determine a stellar age. So one caveat for a lot of the stuff that I'll talk about is the ages that we use in rotational evolution are still model dependent. People have done isochrone fitting to get cluster ages, but basically they've used different isochrones for different different clusters, and for the most part, some of the models that I'll show are still calibrated on younger ages. So that's why some of the ages may not be quite what you're familiar with when I talk about them. So back to ages of individual stars. So back in 1972, Andrew Skumanich published this 1.5-page paper where he showed that lithium rotation is measured by V sin I, and magnetic activity measured in the calcium H and K lines decline at about the same rate with stellar age. I should point out that he did this with 3 data points. This is the Pleiades, this is the Hyades, and this is the Sun. Maybe a bit questionable, but this was the first hint that we could use rotation and activity as a way to determine a star's age. And so the reason that we think activity and rotation, at least, are so closely linked is due to this magnetic dynamo. So this is the sort of Babcock-Leighton dynamo cartoon. So if you start with a colloidal magnetic field and you set the star rotating, the sun is differentially rotating equator moves faster than the poles, so the magnetic field gets twisted up. And eventually, buoyant loops of field rise through the surface. This is where you get sunspots, and non-thermal heating across those loops is how we get excess emission that we measure as magnetic activity. And eventually, these loops reconnect. So if we take these two loops here, if they get close enough, they will reconnect, and you'll get one loop remaining on the surface, and some material and magnetic field being sort of blasted away from the star. And so as the star gets older, it starts to spin down, and as it, oh, wait, I'm getting ahead of myself. All right. So that's how we go from rotation to magnetic fields. But then this magnetic field, any open field lines we have, carry mass away from the star. And if that mass is being carried away in the plane of rotation, it also carries away angular momentum. So the solar wind carries away angular momentum, the star slows down, so the dynamo gets weaker and the magnetic field gets weaker, but it's still slowing down, so you get this feedback loop where activity and rotation decline together with age. And it does turn out that the Skumanich law works pretty well for solar-type stars. So this is Eric Mamajak's update to Skumanich. So now fast rotation is down. There we go. Fast rotation is down as a function of age. And this is open cluster stars and then astroseismic targets and the sun up here. And so what you can see is that, stellar rotation still appears to decline as t to the minus 1/2, roughly, for solar-type stars. The pre-main sequence is additionally more complicated. I'm not talking about that at all, but that's one of the things that I'm working on currently. But if we want to look at K and M dwarfs, which are going to be sort of our most common planet hosts that we'll find, things get more complicated. So this is a model where we have 3 stars that start at the same rotation period. Faster rotation is up again. And if we look at the solar-type star on this black line, it spins up on the pre-main sequence as it contracts, and then it spins down again. And that spin down is still roughly Skumanich-like. But a lower mass star, say half a solar mass or a 0.1 solar mass M dwarf, these are much more complicated. They spend more time on the pre-main sequence, so they spin up for longer. And then their spin down is definitely not just a simple power law. So we need to use open clusters to calibrate what's going on with these K and M dwarfs. So if we look at a young cluster, this is the Orion Nebula cluster, an NGC 6530. So stellar rotation period as a function of mass. Mass is going the wrong way because lower mass stars are over here because they're redder, so it matches like a B minus V. And we can see that in this cluster, stars of all masses have a range of rotation periods between about 1 and 10 days. So the movie that I'm about to show you is Sean Matt's 2015 model. To start off, he uses a distribution that's like that ONC distribution I just showed. And so what you're going to see is the stars will contract on the pre-main sequence, and then as they start to spin down, the higher mass stars will spin down first. So everything now is on the pre-main sequence, spinning up as it's contracting to conserve angular momentum. Higher mass stars reach the main sequence first. Ignore the lines that are going to pop up in a minute. And what you can see is that these higher mass stars are converging onto the single-valued slow rotator sequence, but at lower masses, you still have a spread in periods. So there's 2 things that we're looking for when we're looking to calibrate rotation as a function of age. One is the shape of this envelope that becomes that single-valued slow rotator sequence. And one is that transition between a slow rotator sequence and a distribution of periods at a given age. And so if the models worked really well, we could just use those to figure out the ages of field stars, and it would be great. But the difficulty is that we don't have a lot of constraints on evolution at older ages. So this is NGC 6811 at 1 gigayear, and prior to this year, we only really got down to the K, maybe mid-K in periods. If we go to 2.5 gigayear, if we include an IMPREP paper by Jason Curtis, we can maybe get to the M dwarfs. And you can see that that slow rotator sequence is moving upward here. And then we get to the sun's age in M67. So there's the sun. And a few more periods have been added here, but they're still all at higher masses. And so we don't have any constraints with open clusters for the low mass of stellar evolution. We do have a lot of field stars with rotation periods from Amy McQuillan and Elizabeth Newton's work, but we don't have ages for these stars. So figuring out sort of what's this gap here, what's this gap here, we rely on sort of large-scale statistics, and we're not going to get very precise ages out of these stars. So my work thus far has mostly focused on the Hyades and Praesepe open clusters. These are the oldest open clusters where we can observe a large ensemble of M dwarfs and know their ages. So before K2, this is what the rotation period distribution in these two clusters together looked like. So we can see where the slow rotator sequence is. Maybe we can see where you start to get that fanning out of periods, but something's over here, something funny's over here. There's still a lot of questions here. So as I said, the Hyades and Praesepe are our nearest open cluster neighbors, or oldest open cluster neighbors. So this is cluster age as a function of distance from the sun. The Hyades is the closest open cluster to us at 47 parsecs. Praesepe is still relatively close, closer than most of our other neighbors. So the question that we want to ask is, what's the rotation period distribution in these clusters? So if we're looking at the sun, for example, we can watch star spots go around and around. And even though the lifetime of star spots is about on the order of a rotation period, we can get a decent estimate of the sun's period just by watching spots go around. But on other stars, we can't resolve these spots. So all we can watch is for the star to get brighter and dimmer in a roughly sinusoidal way to measure rotation periods. So if we go and look at the Hyades, you are all pretty familiar with this cluster because it's just the head of Taurus. Aldebaran is unassociated. It's 47 parsecs away, so it's nice and bright. We can get a lot of other measurements like X-ray and UV, but it's really spread out. Hyades stars cover about 70 degrees in both RA and DEC on the sky. There's less than one Hyade per square degree. So trying to survey it is really challenging. So in the 80s and 90s, Radek and Prosser did individual studies of rotation for mostly solar-type stars. We got 10 or so. Then, 8 or 10 years ago, we started adding these large-scale transit and transient surveys. So WASP and HAT did include a lot of Hyades, and so we started to fill in the slow rotator sequence here. That's all these gray points. The K2 completely changed the game. So when the Kepler mission broke, the reaction wheels broke, and they had to point in the ecliptic. It was unfortunate for a lot of exoplanet studies, but really great for my thesis. So as I said, the Hyades cover at least 70 degrees in both RA and DEC. And between K2 Campaign 4 and Campaign 13, it surveyed 196 Hyades in the cluster core, which is huge. There were only about 80 periods known before K2. And so from Campaign 4, my 2016 paper, we measured for the first time rotation periods for a large number of fully convective M dwarfs in the Hyades. This is our nearest open cluster neighbor, and we did not have rotation measurements for its lowest mass stars. And then Campaign 13 added a whole bunch more periods as well. And so in total, we added 131 new periods to the roughly 80 that were known before. Praesepe is a little bit further away, sort of a twin of the Hyades, not quite the same age. And it's about 180 parsecs away, and it is more compact, but it's still about 7 degrees across. So this is blue are Praesepe stars targeted in Campaign 5, gray are other stars, and these green squares were the footprint from the Palomar Transient Factory survey of Praesepe in like 2010, 2011. So they were able to cover a lot of the stars, but the precision maybe wasn't quite as good, and it took a lot more effort than just 70 days with K2. It took a couple winters. So with just from Campaign 5, there were 794 out of about 1,200 Praesepe stars in there. And we added 471 new rotation periods. So these are just some of the phase-folded light curves from that campaign. And you can see there's sort of a wealth of spot indicators and variability going on, which I'm not going to talk about at all, but is definitely ripe for investigation if anyone is interested in that. So, all right. I put these out of order. All right, sorry about that. So gray points are the periods that existed before K2. Red are the points that we added from K2 campaign 5. And then, it did my animations backwards, I'm sorry. These red points now are new periods from campaign 16. So campaign 16 had kind of an offset field of view. These were measured by Raina Rampali, who's a post-bac student at Columbia right now. She's still working on quality control on these, but we still have added about 100 new periods. Okay, so now that we know what the roughly complete distribution of rotation periods is at about 650 million years to 750 million years, can we accurately predict what those periods are with our models? So again, this is Sean Matt's 2015 model, and so, spinning up on the pre-main sequence, and then what we're basically going to do is, once we get to about 650 million years, then we'll compare to Praesepe. So that's about here. So for those 2015 models, this is so the black is Hyades and Praesepe, and the green is the 2015 models. And so some things work really well in this model. Slowly rotating FG and early K stars, it's matching that envelope pretty well. Interestingly, also matches fully convective M dwarfs. However, we also observe this enhanced breaking in early M dwarfs. So this model predicts that all the M dwarfs should be rapidly rotating. But it turns out that at least 60% of the early M dwarfs in this cluster are actually slowly rotating. They're more slowly rotating than the model predicts at all. And we can also see this if we compare with the Pleiades. So now the green points are Pleiades from Louisa Rebel's paper. You can see that roughly you have a mostly even evolution from Pleiades age to Hyades age. This is a bad mass conversion. But all the Pleiades early M dwarfs are rapidly rotating, about where the map models predict the Praesepe stars should still be. But instead we can see that they've actually gone through a pretty significant rotational evolution across this age. And so we think what's happening here is something about their magnetic fields of these M dwarfs is they're configured in such a way to make their braking more efficient than if you just project a sun-like wind onto them. And so these are new results. So Sean has gone through and changed the stellar wind prescription in his models to make braking more efficient for some of these rapid rotators, and things are looking a lot better. So you can see that now we're still missing the slowest rotators up here, but the model is getting closer, and it's also reproducing this sort of possible underdensity of periods in these intermediate ranges. Dearth of stars in these intermediate periods. This is just a slightly older model. It still looks about the same. The slower rotators aren't matching quite as well. So one other assumption that was sort of plaguing the models that I already showed, and is still a problem, is that this assumption that all FG, K, and M stars spin down in the same way. So if you have sort of this shape for the slow rotator sequence, that's just going to move. It's going to follow that t to the -1/2 spin down law, and all these stars will obey that in the same way. So this is the log period scale that I've been showing before. I'm going to switch to linear period for the rest of the talk because it makes some of these things easier to see. These are the same models. So that t to the minus 1/2, it does mean that the lower mass rotators do spin down sort of more quickly, but they're all obeying that same braking index. But the reality that we're seeing is that even clusters of similar ages can have different period distributions, and their slow rotator sequences will have different shapes. So this is work that Jason Curtis and I have done just this year. So now showing rotation period is still faster going down, but now this is showing effective temperature. Blue are Praesepe stars, and orange are Hyades stars. And this black line here is a fit to the Praesepe slow rotator sequence. So just to zoom in a little bit, this blue line was the black line on the previous page. So this is sort of the median rotation period distribution in the Hyades, in Praesepe. And you can see that the Hyades stars all tend to fall above it. These open diamonds are binaries or possible non-members that we removed for this study, but we removed them before we ever looked at the rotation periods. And so what you can see is that since the Hyades stars are rotating more slowly, in terms of thinking about angular momentum evolution, that means that they're a little bit older. And it turns out that at least for solar type stars, this difference corresponds to a roughly 57 million year age difference, which is also pretty much exactly the same age difference that we see if we just look at isochronal ages for the two clusters. So we can actually see this evolution happening on relatively short timescales. However, so now what we're looking at is the differential rotational age of the Hyades minus Praesepe. So Praesepe is at 0 in the gray line, and the orange points are the Hyades, and the black line is just a rough fit to the Hyades. And so for the solar type stars that we were looking at before, we do see this definite rotational age difference between the two clusters. But it disappears when you get down into the K-dwarfs. So even though we can definitely see rotational evolution happening over less than 60 million years, for solar type stars, nothing is changing for the K-dwarfs. Somehow their rotation has stalled. And this stalling continues for at least a gigayear. So here now, dark blue is the Pleiades, the cyan is Praesepe, and the orange points are NGC 6811 with a new extension down to about M0. And you can see that, again, the solar type stars are continuing to evolve. They're continuing to follow the Skumanich law just like we expect. But the K and early M type stars aren't really evolving at all. Something is causing them to stop evolving. Their rotation stops evolving. What we think that is actually internal angular momentum transport. So these are new models by Spada and Lanzafame. And so it starts at about 100 million years and goes up to solar type age. And so if you compare that to the models that we were looking at before, now the shape of the slow rotator sequence is changing, where they've included the core often stays rapidly rotating, or is believed to stay rapidly rotating. And so what we usually observe is the outer envelope breaking. But at some point, you start to get angular momentum being transported out of the core again and into the envelope. So at that point, you get a competing effect where even though the magnetic field is trying to slow down the envelope, it's also being sort of rejuvenated internally. And those balance for a while until magnetic braking takes over again. So up till this point, models have been missing some pretty important physics for K and M dwarfs from at least about 100 million years to 2.5 gigayears, but that is starting to change. Models that are just coming out in the next sort of 6 months to a year have started to include better magnetic field prescriptions for M dwarfs and better internal angular, or any internal angular momentum transport, actually. Most models use a solid body up till now. So the other question that I've been focusing on is how do binary companions affect a star's rotational evolution? So if we look back at this model comparison, we have these outliers among the FGK stars. And it turns out that these are actually all binaries. So or basically all binaries. So open symbols here are candidate binaries, crosses and pluses are confirmed binaries. And pretty much all these outliers, like I said, do have a companion of some type. So this affects our analysis in a couple of ways. One is just it biases our data. So now this is just going back to the Heidi's post-campaign 4 for a minute. So if we have 2 stars, but we are pretending that, or we think that there's only 1 there, then that's going to bias our mass estimates because the binary is going to be overluminous relative to a single star. And so we'll estimate the masses to be too high. And so these stars should really be to the right on this diagram. We also have a problem where a lot of the stars, especially that we observe in K2, have 2 rotation periods that we can see. And even if there is only 1 rotation period, which star does it belong to? Does it belong to, if you have a G dwarf and a K dwarf in the same, so relative brightnesses comes into play. But if you have an M0 and an M2, you don't know which period you're looking at. But there also is a physical reason why this is happening. So there's been some indirect evidence for a long time that stars and binaries rotate faster than single stars. So this is a 1994 study of X-rays in the Hyades, and the X-ray luminosity function of single stars binary stars is much brighter than that of single stars. This suggests, if they're more X-ray bright, that suggests that they're more rapidly rotating. In Patience et al.'s study of Alpha Per, she found that wide binaries had low V sin i's, so they're slowly rotating, but the handful of closer binaries that she had within about 60 AU were all rapidly rotating. And so why would this be happening? Well, one possible cause is due to tides. So if you have a primary star here with a companion, the companion raises a tidal bulge on the star, and then those 2 bulges experience different forces, or different gravitational forces due to the secondary, so there's a torque on the primary, and eventually the primary's orbit will be synchronized with the tidal bulge, so the orbit will be synchronized to the rotation period, and the orbit will eventually circularize. But this only affects 1% to 2% of binaries in clusters, only those with orbital periods less than 10, maybe 15 days. So when we're looking at wider binaries, there has to be something else going on. And the probable reason for this is due to stellar disks. We had a couple great disk talks yesterday that were mentioning that when you have a protostar or young star with a disk, it's accreting material along its magnetic field lines, but those also can lock it to the disk, or at least this is what we think. And so the disk acts as an angular momentum sink. As the star contracts, to conserve angular momentum, it should spin faster, but if it can transport angular momentum to its disk, it can contract without spinning up at all. And so this is usually what's used to explain why there's that 1 to 10 day distribution of periods in very young clusters, is that the rapid rotators had lost their disks earlier. So how do binaries play into this? Well, so a binary companion can disrupt or alter disks. So this is a cartoon that is wildly not to scale, but just to give you a sense of what is roughly happening. If you have a single star and it has a disk, and then you put another star next to it, maybe in a close binary it totally disrupts the disk, or you could end up with a circumbinary disk where both stars are in the center of this disk of material. For a moderate separation binary, maybe both stars have smaller disks, maybe only one star keeps its disk. And wide binaries, at some point they just are behaving like 2 single stars. Their orbits are too wide to have any kind of gravitational or photoevaporative interaction. And we do see evidence of this. So this is Louisa Rebel's 2006 paper, where this is infrared excess. So these stars over here are disked. These don't have disks. Rapid rotators tend to have no disks. Slow rotators actually bridge both sections. And if we look at binaries, Sayes et al. 2019 or 2009 found that so this is binary separation here. Within about 40 AU, binaries preferentially disrupt their protoplanetary disks. So this is probably of order the sort of separation regime where we expect to see the strongest effects on the ultimate rotation period distribution. So the first person to look at this with both direct evidence of binaries and direct measurements of rotation was Søren Maibaum. So this is binary period, this is for spectroscopic binaries. Binary period, removing stars that may be tidally synchronized. This is rotation period. So binaries are the black histogram. Binaries wider than 5 AU and RV non-variables are gray. And what he found is that on average, these binaries rotate twice as fast as single stars and wide binaries. And so trying to confirm this result, because again, this 5 AU is way closer than binary studies suggest is the critical range for this sort of disk disruption or not disruption to be happening. So what I'm working on is binary surveys in open clusters to try to investigate, try to figure out where exactly is this cutoff where you get faster rotation in binaries versus not. So in Praecipe, for example, we have a bunch of ongoing studies. So this is just, gray background is just all the rotation periods that we have so far. Circles, candidate binaries, crosses confirmed. So K2 has brought us new eclipsing binaries. Many of them are M dwarfs, which is really great for calibrating stellar properties. There's an ongoing wind hydra study that Natalie Gosnell and Andrew Mann are leading that Maddie Lucy has also been a big part of that has found a whole bunch of spectroscopic binaries, mostly among M dwarfs. Sam Quinn and I are working on a survey with TRACE, the TRACE spectrograph of solar-type stars, and we found quite a few binaries and candidates at the higher mass solar-type end. RoboAO has added a handful, Hillenbrand 2017. And finally, I've been working this past year, or we did the observations in December of a KEKAO survey of early M stars in Praecipe that I've been working on with Adam Krause, Aaron Rizzuto, and Andrew Mann. And so just to take a look at these purple stars in particular. So this is projected separation in milli-arcseconds as a function of rotation period. And this is the 80 AU. This is what 80 AU corresponds to at Praecipe's distance. So the purple dots are all of our detections from our 2018 B observations. The crosses are probable contaminants based on Gaia data. They have very different parallaxes or proper motions compared to the primary. And so what we can see is at least where we have detected a companion, the rapid rotators here all seem to have a companion within about 80 AU. This is good. This suggests that maybe the cutoff for where binaries start to have an impact on disks is about 80 AU, which is consistent with some prior studies. Now we can also add, these are other archival Keck observations, as well as in orange, that RoboAO data. And this seems to be holding up. There's a couple of potentially funky stars up there. This does seem to be holding up. And so this is consistent with the results that Messina et al. Found in 2017. So this is showing basically things within these dashed lines are the slow rotator sequence. This is binary separation. And they found that all of their rapid rotators were in binaries with separations less than 80 AU. So this suggests that we are really onto something. I'm still a little bit concerned about the size of the samples that we have. So this is something that I'm working on going back to get more data for, but it is pretty suggestive. And this does also match with the observations of planet occurrence rates in binaries. So Adam in 2016 found that for binaries less than about 47 AU, you get suppressed planet occurrence rates. So this is still an ongoing problem for models of rotational evolution. All these models just assume that you have a single star that's evolving in isolation from the time that it's born. But it's possible that we're actually seeing results that indicate different initial conditions for stars depending on whether they have a binary and how far away that binary is. So what's next? This is kind of a smorgasbord of the too many projects that I have going right now. So the first thing that I'm working on is trying to figure out what's going on with this KEC data and whether it's actually significant. So what I've now added here, this is back to just my, just the detections from my work or from this wind survey. And I've added down here, these arrows indicate, they're not really upper limits, but they're the rotation periods of stars where we did not detect a KEC companion, even though we may have looked for it. So purple are things where we have both KEC and wind data. Blue is just wind data. So there's a couple interesting things. One is that we still have quite a few stars that are rapidly rotating but don't have a binary companion. And so we need to figure out what's going on with those and where, if our detection limits are causing the problem or if it is a physics thing. The other thing is that it's hard to see because all these figures are, all these points are crowded. All of the close spectroscopic binaries, we don't have orbits, but the stars with the highest radial velocity variability, they're all slow rotators. So that's weird. Because we expect that even based on, say, Soren's old work, we expect that even the spectroscopic binaries should be rapidly rotating. But they aren't. And we actually also see this in Willie Torres's Pleiades data for solar-type stars, where the very closest spectroscopic binaries also appear to be slowly rotating, even when tidal synchronization isn't at play. So if we look back at this sort of cartoon of what's maybe happening with the disks, that suggests that possibly for these slow rotator, or sorry, for these close spectroscopic binaries, that they're actually mostly occurring, basically they're not disrupting their disks that much. And this is consistent with theoretical work by, say, Alexander 2012, that when you get these two binaries that are so close together, both the gravitational and photoevaporative UV effects on the disk are actually reduced. Other work that I'm doing is going through a lot of Soren Maibaum's old hectoshell data and looking for binaries there. So this is NGC 6811. The rotation periods are shown in gray. Quality hasn't been filtered, unfortunately. So all these colored points are new binaries where we have measured the orbital period. We have a handful of synchronized binaries down here. These might be getting close. And you can see they're at kind of a range of rotation periods. And as I said before, we have I have a whole bunch of new and ongoing binary surveys using, or that I'm leading or part of WIN, MMT, TRACE, KEC, and Gemini South. So I'm also working with young open clusters using speckle imaging at Gemini South. So just to conclude, my work has shown that 650 million year old early M dwarfs rotate more slowly than predicted, which suggests that they're undergoing more efficient magnetic braking than we would expect based on solar type stars. But also, spin down stalls out for K in early M dwarfs from 600 million years to at least a gigayear, suggesting that we're seeing the core and the envelope recoupling, and the core is transporting angular momentum back into the envelope. Also, most rapid rotators are at least candidate binaries, but also we're seeing evidence that close binaries rotate slowly. So one of my big questions for my research going forward is what is the relationship between binary separation and rotation period? And so I'm currently working on 8 different surveys, or surveys of 8 different clusters to find new binaries. Thank you.
Okay, we've got a few minutes for questions. Yes, that was a very immediate hand.
So, might be a difficult question, I'm not sure. Do magnetic fields then evolve through time in terms of their strength and extent? Mm-hmm. Is that what we're seeing with these kinds of stars, that the magnetic field is reducing more rapidly?
Yeah, so to answer the first part of your question, yes. The magnetic fields do evolve with time, both in strength and also probably in configuration. So one idea that Cecilia Garafo has been working on a lot is that rapid rotators have these much more toroidal, so twisted up magnetic fields that don't break very well. And so that's why they sort of hang out at rapid rotation for a while. And then once they sort of develop the larger scale fields, they can break more efficiently. And then, so part of what we're seeing is a change in strength. But can you say again the last part of your question? Because I feel like I'm gonna not answer it right.
So it was more along the lines of if they're evolving through time, is that the reason why you're seeing much slower rotators, that they more rapidly lost their magnetic field strength?
Yeah. So it's part of that feedback loop. So as they spin down, their dynamo gets weaker, so their magnetic fields get weaker, and their braking is less efficient. So that's why you get that. That's why they all converge. So initially, the rapid rotators brake more efficiently, so they start heading to slower periods, but they never cross. They don't cross the slow rotators and keep spinning down, because as they reach the same periods, their magnetic fields become more similar, and so then they start to spin down together after that.
Great, thank you.
More questions? Yeah, great.
I didn't see you mention the test data set at all. Do you think that's going to add to your analysis, or is it just repeating something you already had?
No, test is actually going to be really great, and the reason I haven't talked about it is just because we don't have results for it yet. So I currently have a student who's working on measuring test periods for 6 young open clusters in the south. They're the same clusters that I'm targeting with Gemini for speckle imaging. And they're at a really key point in rotational evolution for solar-type stars where right around the zero-age main sequence for a sun-like star, these rotational evolution models are completely unconstrained. There are no published periods for solar-type stars at that age. So actually, one of the modelers was asked if we could go find those. And so that's what we're working on right now. There's a few other young clusters in the north that are sparse enough to look at. It'll also be really great for star-forming regions. Some of them are sparse enough and a little bit far enough out of the galactic plane that we'll also be able to look again at a lot of these young clusters that have disk and binary surveys that were talked about yesterday. Test will be great.
So,
in terms of differences between binaries and single stars, I'm wondering if there might be differences in the initial rotation rates, say, due to formation, or whether that kind of signal would be lost during the spin-up phase.
Yeah, I think this is something that we don't really know yet. Getting any rotation periods out of young stars is actually still... No, that's not right. Yes, that's not quite clear yet. I think the data is getting there. There have been, like I said, a ton of binary and disk surveys in the last few years, especially now that ALMA's coming online, and they've done these Spitzer legacy surveys that I think we actually can start to investigate that question because at some point, right, single stars also disrupt their disks, and so the timescales for that are also are feeding into this a little bit. So yeah, we're sort of poised to be able to disentangle those effects.
great. Maybe one more question? This is illegal.
So yes, I was also curious about the rotation rates of the spectroscopic binaries and how they're not as fast as you might expect. I was wondering, like, I know it's probably still early days, but if there's any trends that were emerging between maybe the periods or separations, and whether there's a trend with period or separation.
Yeah, so this is still pretty fuzzy because the data sets are sort of a pretty mixed bag. So I know with Willie's Pleiades data, when I selected for the spectroscopic binaries with periods 100 days or less, those were all in the slow rotator sequence. So I know that was one of the things that we saw, which doesn't gel at all with Soren's M35 data because it's the same mass range. So yeah, it's still very tentative and very small numbers, but so it's definitely something that needs to be investigated more.
For the same 70 again. Okay, we've got a coffee break now.